All right, excellent. So when we left off about 3 weeks ago at week 4, we're just getting started on some sort of analytics modeling and how it pertains to adding value to the business. Week 5, you're on your own. And when you're on your own, you are doing some sort of entry to analytics. And one of the things we do is something called Monte Carlo simulation. That is in itself, for lack of a better word, a simulation where you have many variables and you choose the variables based on the distribution and you try to project. I went ahead and recorded some videos. Hopefully you had a chance to look at it. One of them shows how to do simulation from an Excel point of view. The other one that you already have part of your lab package does it via Python programming. So at a fundamental level, simulation tells you if you are doing the same thing over and over and over again, let's say 1,000 times, 10,000 times, 20,000 times, whatever it is, what are the chances? What are the chances of something being positive or negative or neutral? In other words, if you're doing simulation when it comes to businesses, is the business going to be 50% of the time positive, 25% of the time negative, and 25% of the time breaking even? So it gives you some idea. So as opposed to just one shot, you're looking at multiple different areas. For example, if you're shooting basketball, right? If someone told you that I really want to know how well you shoot the basketball when you take a ball and you try to put it through the net. If they only gave you one shot to see how well of a basketball shooter you are, that sounds a little difficult, because what if you miss it? Then your record is of almost 50%, right? But if someone said, take 50 shots, and based on the 50 shots, let's try to assess how many times you'll make it and how many times you won't make it, then that is a better thing because it gives us a large sample size. Monte Carlo simulation
Why
does.
are you finished?
Hmm? Oops, sorry, I'm getting some feedback. Very kind reminder to turn off your. Sorry. Oh, okay. I think someone. Okay, not a problem. Just make sure you're muted, because then I get to hear your thing I recorded later, which is no fun. So what I was saying is that if you have a bigger sample size and you can get an idea on how well you're doing. So Monte Carlo simulation is named after Monte Carlo, the casino. And what it says, essentially what it does is it looks at descriptive statistics like average, mean, standard deviation, and it will not just randomly give you projection, it will give you projection based on distribution of data. So if you're running Monte Carlo simulation, you need to know the distribution of your data, which you've done it already. If you just kind of plot the data, you should have some idea about distribution. Is it normally distributed? Is it uniformly distributed? Is it binomial? Things like that. You'll get used to it as you do it. So once you know the distribution, once you know a little bit of information, it will give you projection based on the boundaries. So essentially, if you go to the basketball example, it will say that, I mean, looks like this person is going to shoot on an average 50% of the time and makes the shot. Perhaps the person will miss shots from different angles. It has that data and it'll bound those projections based on that. So when you're looking at Monte Carlo simulation, it won't really give you data all over the place. It will give you projection based on your distribution. So it is a really good way of projecting. I highly encourage you to use it if you're maybe running an Amazon store online, or maybe perhaps running some analysis at work, maybe if you're working in supply chain and so forth. So it is a really beautiful tool. And as you can see, there's a lot of information. You can draw it up, and it just gives you a nice and warm and fuzzy feeling that you have actually simulated and seen, right? If you watch sports, sometimes they also talk about simulating um, the winner. So, they will say 10,000 simulation and maybe Germany will win the Euro 2024, something like that. And that is what it is. It will take out how Germany is performing, what kind of team state has played, what is the record of the team. It has a distribution of that data. It takes it in and it will kind of project. I'm not saying they use Monte Carlo simulation, but it could be one of the simulations, something like that. So as I paused, that was kind of like a brief 2-minute spiel on last week 5's content. At this point, I have also graded your project 1 sprint. Hopefully you had a chance to go through that. Most of you did a wonderful job. Maybe a little more visualization, maybe being a little adventurous with using different kind of plots would be awesome, because images tell you much more than words. Sometimes it's just easier. There's a lot of dynamic visualization techniques in Plotly where you can drag and drop, and you can do a lot of interactive tools within your HTML output. So maybe you can try that. This is not a must for your course, but something you may want to look at. The other things you can also do is, like, maybe you're dealing with a lot of Excel data. You can put Excel on the back end, and you can use your Python to grab data and run it. So maybe I'll post a video on how to do it. Like, for example, let's say you have 100,000 entries and you don't want to open the Excel or CSV file. I'll maybe create, like, some sort of Python file where you can actually grab the file and do your processing without actually needing to open that kind of stuff as well. So I'll take a pause here, and I'll entertain some questions, if any, regarding your Sprint 2, or well, Sprint 2 may be very similar to Sprint 1, but anything that you wanted to ask or speak about. I did look at the peer review, and if peer review, once again, is anonymous, if someone had to dispute their grades, I would not disclose how you graded them. That would be not a good thing. So don't feel obligated. Don't feel anxious that you're going to make some enemies. That's perfectly fine. I adjusted grades based on your feedback, collective feedback. So so your grades are kind of like individual stuff. I mean, some of the times, if you're doing the same thing as group members, you'll be getting the same grades. But in some cases where there was no participation or no effort, I gave them as low as 0. I cannot give negative, wish I could, but I can't. So your grades are adjusted that way. So anyway, without further ado, I'm going to open the chat or the forum for, if you have any questions. I'll pause here for 10 seconds, and I'll also get an opportunity to drink some water. All right, looks like I'm going to check the chat as well. Okay, looks like you guys are fairly, don't have a lot of questions, but you can always email me if you do. All right, let's go to the week 6 content. In week 6, we're looking at, I'm just going to pull this here. We're looking at the idea, and if you look at the value chain, the cascading, little modules that we're looking at, from data to information to analytics, all the way to creating value, they work in, they work as a symphony, in the sense that every little thing has importance going up as well. So bad data essentially cannot be turned into information, and obviously the information, if you're fundamentally wrong about sourcing your data, the analytics are not going to be accurate or useful at all. So what is analytics? This is a term that is thrown around quite often: business analytics, sports analytics. We're dependent on data, we're dependent on this, we're dependent on that, and so forth. Analytics at a very high level is about using data, obviously, and the data is constructed or fed to a model. And what is a model? Model is essentially your way of doing things. So if you're saying, if you have an Excel sheet, and if you say if else, if you see something, do something, that is a model itself. It could be as simple as that. A model is your a tool. Model is your spreadsheet. Model is your Python code. Model is your thought process that when you feed data, it can give you some predictive, prescriptive, or whatever analytics that you choose to do. When it comes to modeling, there's a lot of models, obviously. There are a lot of different algorithms. And one point to notice, sometimes we use terms like algorithms and models interchangeably. The distinction here is model encapsulates more than algorithm. So it could have algorithm, it could have data cleansing, it could have a lot of different things. Algorithm is a specific way of doing things. Algorithm is a set of rules based on previously vetted, previously proven context. So today, week 6, we'll be looking at a bunch of different way of constructing models based on the data we have. We're also looking at one of the most oldest modeling or algorithm, which is called linear regression, which some of you may have encountered in your previous life or previous educational journey. It is one of the most simplest way of assessing things. And eventually, we'll be starting our analytics journey, well, very least with the linear regression context. So you may see a lot of different topics engaged today. One of them is analytic modeling, using data to create something. A machine learning. Machine learning is about learning from historical data and projecting and doing something. The distinction here with machine learning and AI is that AI is a general term. Like, AI could be your robotics, reinforcement learning. AI could be natural language processing. AI could be machine learning. And machine learning is specifically based on the foundational idea of statistics. So if you had a lot of data and you created some sort of rules and you told the rules to do something, that is machine learning. It is learning based on previous data, right? So machine learning has a lot of different algorithms that we can use. If we were only to go with all the algorithms uh, um, that is available in the literature, it may take us a year. So every person will create, every researcher every now and then will create different kind of algorithms, and the algorithms are just all over the place. However, there are just some foundational algorithms that we can potentially use. Something called linear regression, logistic regression, and decision tree. Some of these things we'll try to indulge and investigate. So today, we talk about modeling, and the other terminology also is something called data mining. Data mining is kind of similar to your gold mining, right? If you are in certain parts of Canada or Africa, there's a lot of mines. You filter through or you shift through a lot of dirt, a lot of stones to find those gold nuggets. That is mining in the purest sense, physical mining. Data mining is also the same thing. You're looking at large free text like your Google review, your Yelp review, your Amazon review, customer comments, PDF contents. And based on that, you mine to find important information. So you have large hoards of data, and based on that, you will just quickly go and grab things that are important to you. Perhaps an example of data mining is you may want to know what are some of the common phrases people are using. Or you may also want to know what are some of the common terminologies or words people frequently use, or what is emphasis about certain words, or is the context negative or positive? So these are some examples of data mining. Eventually, we'll finish off our week with Python 6, Lab 6 on Python. I've already pre-recorded the Excel and Python related video on YouTube already. I've already put it there. The reason why I wanted to do that, the course does not require you to know from an Excel point of view, but I do understand that a lot of us use Excel more often, and a lot of things that Python can do, Excel can also do, but Python is better when you're scaling to large data, whereas Excel is limited to certain rows and columns. But the fact that we are always seeing Excel on a daily basis, I wanted to give you some that bridging concept so that you can try it out on both sides. If you're fairly uncomfortable with Python, maybe stick with Excel. But if you want to try both, you can do that as well. So those are the topics we'll be kind of talking about on today's lecture, and I would highly recommend you to um, um, kind of try labs on your own, because without that, it's quite difficult. So what is analytic model? Modeling rather. So, models are in some ways representation of reality. You are given data, let's say supply chain data, and you understand some sort of correlation, which we covered last few weeks. You understand that, let's say you're given, ice cream sales data. It is really warm, and you realize that ice cream sales are kind of going up whenever the temperature is heating up. And based on that assumption, you created a model, and you say, if it is 30 degrees Celsius, you will be selling 50,000 cones of ice cream or 50,000 buckets of ice cream, whatever. If it is 40,000, you sell a little less, and so forth. In essence, you created a model. Now, next time a shopkeeper comes and says, can you project and can you predict me how much ice cream I'll sell if the temperature is about 25 degrees, let's say. You can give them a projection or prediction based on the information that you have. So what we essentially did was create a model, and we can create that model through simplification, because we simplified a larger problem. And we also made a lot of assumptions. One of the assumptions we made was that the relation or correlation between temperature and ice cream. Perhaps there is no correlation. Perhaps the ice cream is being sold more because there's maybe new flavor being introduced. Perhaps it is sugar-free. Perhaps it is really healthy, protein-heavy. We don't know. So a model can only do so much. A model cannot encapsulate your entire world. That one variable that we are talking about is what we call independent variable. That independent variable, temperature, dictates how many ice creams are going to be sold, or a dependent variable. If you can just think about those concepts, you can quickly assume that all models are probably wrong. So whatever you are doing, whatever OpenAI is doing, whatever Meta is doing, whatever Amazon is doing, whatever the most smartest companies and scientists are doing, is absolutely going to be wrong. All models are absolutely going to be wrong. The premise we have is the models can be wrong, but our job is to ensure that we are somehow closer to the truth than the other way around. Maybe we can project the ice cream sales plus minus 500 ice creams. Maybe we can get to that zone, but we can never be precise. Think about it, right? Like, if you notice, Michael Jordan's parents, Michael Jordan, the great basketball player, his dad was 5'7" and your mom was 5'4". If you created a model to check or predict Michael Jordan's height about 60 odd years ago, you would look at his mom's height, dad's height, his brother's height, uncle's height. And it turns out most of his family members were relatively short. Most of them were under 6 feet tall. You would nowhere be able to guess that his height was going to be 6'7". That is when the model would be wrong. Our general assumption is that when parents are tall, the children or child is also going to be tall. It is probably accurate most of the times, but in some cases, it is not accurate. In some cases, potentially the model didn't encapsulate the child's genetic issues. Maybe the model didn't encapsulate the diet the child was taking. There was no way for the model to know. The model also didn't know about some of the, what we call as error in statistics is there's something that is not explainable, absolutely not explainable. You can bang your head in the wall, but it cannot be, it is not explainable. It is such a random thing to happen. So we can create all the models we want, but the challenge is that the models is always going to be wrong. But we try our best to get closer and closer to the truth. If you look at the Michael Jordan's height, let's say, 60 years, we have a time machine, and we created a model to project Michael Jordan's height. And when we created Michael Jordan's height, we wanted to know, so we decided that there's certain things, if you wanted to predict child's height or Michael Jordan's height, we want to know his parents' height, we want to know his dad's height, and maybe we want to know his grandfather's height. Let's look at 3 variables. Those variables, maybe we can use average, maybe we can use some sort of coefficient, whatever it is, you decide. The model is your piece of work. Those 3 heights of his parents and his grandfather is what we call independent variable. The independent variables are fed into the model, and we still haven't talked how the model processes data. And model is an abstract concept here as well. In other words, what we're saying model could be whatever you choose it to do. And based on those 3 independent variables, the model will project a height for Michael Jordan, and we call it dependent variable. You may hear this term quite often in this space, but the best way to kind of never forget the distinction between dependent and independent variables. Dependent variable is always something you want to find. In other words, Michael Jordan's height is dependent on independent variable. Michael Jordan's number of baskets he's going to make in life, if you want to find out. In other words, let me take a step back. Whatever you're trying to find out is always going to be dependent variable. In this case, we're trying to find out Michael Jordan's height. It is dependent variable. But based on what though? Well, based on his mom's height, his dad's height, and his grandfather's height. Those are independent variables. In some cases, you have, they also call it response variable and explanatory variable. So you may hear terminologies, like this. For example, this would also, I'm just going to annotate here. In some cases, you might also, hear some people saying response variable. It means the same thing. And if whatever you choose to use, just stick to one so that you're not confused, or explanatory variables. Right. So either you can call it response and explanatory, or you can call it independent and dependent. More or less, it means the same thing. Excuse me. It also sometimes are, called input. You're inputting, you're feeding information, and outcome as well. Same concept, different type of words. We can also, like I mentioned, you can also use explanatory and predicted, or explanatory and response variable, whatever. I use dependent and independent all the time because it's less confusing. And a lot of literature, academic literature, they tend to use those 2 terms quite often. You can also say predictors and predicted. So, all of those last 4 or 5 variables that we use, same thing. Michael Jordan, we're creating a model, we're predicting guys. We can either call it predictor, we can call it explanatory variables, we can call it independent variables. These are just the terminologies that are used like all over the place, but it really means same thing. Also, sometimes you can also call it decision variables. And in some cases, when you're doing machine learning, they use features. Feature is exactly it. So Michael Jordan's dad's height, you can also call it feature, or also call it independent variables. But depending on different, so the feature and the predicted value and these information, you find it more often used in machine learning lingos, whereas your independent, dependent, those kind of variables you see more used in statistics. So, but in essence, it means the same thing. So the point we're trying to put through here is that for you to predict something, you need some information. That information could be independent variables, features, metrics, decision variables, whatever it is, whatever you want to call it. Try to be consistent on the pairing. If you're using independent, dependent, try to use the same thing. Don't go all over the place. Same thing here. You can also, if you are this context that I'm providing here is if you're doing like supply chain or some sort of modeling, there is one measure of metric and it yields business metric. So going to pause here and entertain if you have any questions so far. We're slightly getting now into how to kind of construct a model. That is our intention, but we're starting with different terminology and different wordings here. I'll pause here for 10 seconds to see if you have any questions. Okay. So analytic capabilities are all over the place, and you really don't need to kind of pay too much attention to this table, to be honest, because we're always throwing a lot of terminologies in this space because everyone wants to do something very cool. But if you really want to understand this, is that analytics encapsulates understanding data, discovery. Analytics encapsulates describing how data looks, diagnosing how data looks, and predicting and prescripting, meaning telling them to specifically do some things. In this space that you're seeing, the table you're seeing, these are sometimes also overlapping. What I mean by that is, if you really want to look at it from a machine learning point of view, forget this capabilities chart. The really three things that you need to understand here is when it comes to analytics and especially machine learning, you're really doing only three things, and the rest of them are just extension of that. The first thing you are doing is estimating or regression. So what is that? Estimating price of gas, estimating the number of international students in Canada, estimating the GDP, estimating number of Toronto Island visitors on a specific day, estimating number of Tesla cars sold, estimating number of jobs available in the market. Those are estimating things. The analytics will estimate what is going to happen. If you are Amazon, you want to estimate how many delivery guys you need on X day. That was estimating. Now, my question to you is, when you're estimating, when I was giving you some sort of these examples, what kind of data I'm talking about? Like, in other words, is there like a numerical data when it comes to estimating, or is it a categorical data? GDP, students, Amazon, Tesla cars, is it a number or is it a category? Maybe that's a better question. Throw it in chat if you're not too comfortable talking on the audio. So a lot of these examples that I've given you, is it a number or is it a category? Is a number. Thank you, Vish. So when you are estimating from an analytics point of view, uh, you are estimating a number. It always has to be a number. The second thing that machine learning does is classification. I'll give you some example. Classifying if someone has heart disease or not. Classifying if we will have recession in 2025 or not. Classifying if the color you choose of a Tesla car is going to be green, blue, yellow, black, or 4 or 5 options. Classifying the fruit of your choice. Is it, if you are given opportunity, would you be eating apple, grapes, oranges, and so forth? So another thing that machine learning and analytics can do is classify things. And based on my examples that I've given you, is it a number or is it a category? I'll again look at the chat if you want to throw it out. So these are price of gas, these are, number of delivery guys, right? A classification, absolutely, it's a category. So, if you go and you check, go to doctor, they can tell you if you have COVID or not. They can tell you the choice of car color, is it or color like the red, black, whatever, yellow. It could also mean classifying means, like for example, if you are checking, pass or fail of a student, right? So if you know, machine learning analytics can do 3 things. One is estimating, classifying, and the third is called clustering, which you'll see in here as well. So I'm going to give an example. If I chose, so let's say we're all in the same class, in the same physical room, and in one corner I have delicious samosas, in the other corner I have juicy burgers, and in the third corner I have a ramen noodles, and I just open the door of the physical class and allow you to go in. Perhaps some of you will be gravitated towards samosa, some of you will be gravitated towards burger, and some ramen. I, in a sense, did not tell you where to go. The smell of the food, the aroma of food, you enjoyed and you just made your way. Maybe 5 people wanted samosa, 10 people wanted burger, and 6 people wanted ramen. This is an example of clustering. In other words, clustering is also in some ways categorical, but essentially I did not tell the model, or in other words, I just allowed the model to predict or cluster where people are going. So in essence, it will just group without explicit instruction, right? So out of these 25 odd different capabilities that I have on the screen, I just wanted to kind of like bring it back and tell you that really they all are doing things, all of these 10, 15, 20 things on the table, and they're all converging or reverting back to these 3 fundamental things when it comes to analytics. Either they're estimating numerical value, either they're aligning categorical outcomes, or either they're clustering things, right? The other thing that you also may want to think about is, I already told you that these were not, so let's start with the third one, clustering. They were not given explicit instruction, and we call it unsupervised. We call it unsupervised learning because we didn't tell the group of people what to eat. We just allowed them. We just opened the door and they just ran and grabbed whatever they wanted. Unsupervised means they were not given annotated data. Annotated means labeled data, and it'll make sense in a bit. Whereas the estimation and classification, how can I estimate price of gas, for example? I'll again revert to the chat. If I wanted to create a model to predict price of gas, how would I do that? If I, have you all looked at Gas Buddy, which is an app that you can look and they're more or less correct about gas prices. If they wanted to predict price of gas, what are some of the things they may be looking at? We don't know for a fact, but maybe they're looking at certain things. What could be some of the things they may be looking at? Yeah, Dylan says historic prices, demand and supply metrics. So, I mean, within his model, we can look at three different variables. Yes, absolutely. And when they are looking at those three variables, they have historical prices, as Adil mentions. Based on that, they created a model, right? So in other words, what that means, it is called supervised learning. In the sense that we told the model, let's look at this historical prices. Look at these prices that were in the past and create some sort of trend analysis, whatever it is, based on that information. So it is supervised. You explicitly told the model what to look. That is supervised. Whereas clustering, we didn't tell. We didn't tell what to eat. For our class peers, right? We just opened the door and they ran. We had no idea. But then clustering tells you different preferences of people based on the sample. Same thing with classification. Let's say we wanted to create a classification model, and we wanted to know if someone had COVID or not. What are some of the things that our model can look into if they wanted to predict if someone had COVID or not? Again, I'll revert to the chat. So if you wanted to predict if some person had COVID, the virus or not, what are some of the doctor would so typically when you go is you go to doctor will check your fever, check the breathing, check the energy level, and let's say he or she has a model, and then the model is your data is fed into the model. What are some of the things the model is probably looking at? It is also looking at the symptoms that was previously stuck, right? So it probably had a lot of data about a lot of different people, millions of people, and based on that data, they kind of said, okay, if someone had a temperature over 102 or above, their oximeter was showing less than 90, and so forth, maybe they had a COVID. So in this case also, it is something called supervised learning. So we told the model explicitly what to look for, right? Does it make sense? Because this is kind of like a simplified and more important context or conversation that we need to have before we move forward. Does anyone have any questions regarding the distinction of three analytics purpose, regression, classification, and clustering, and within that also the differentiation between supervised and unsupervised learning? Do you guys have any questions?
Good question, Pip.
Sure.
So let's say when we come to clustering, if we actually had data that actually provided, let's say, ethnic background, and then kind of food that they like, and preferences, would that still be considered clustering or unsupervised learning? If we have to take the same example, like a room full of samosas and ramen and those things, does that still I mean, satisfies that definition?
Yeah, so let me give you an example here. Maybe so for example, let's say you have a table. You can see me draw, right? So let's say you have a table and you have a lot of data. And the first data says like Adele likes samosa, yes or no, yes. Judy likes samosa, yes or no, no, right? So what supervised does is, let's say this is about 1 million entries, meaning that it has a lot of data. And what this is telling you is that when the model, so this is an example of supervised learning. And what the model is saying is, okay, learn from Adil and Judy and look and all their peers and see if they like samosa or not. So this is what we call supervised. We've already told Adil is supply. I'm just making this up. Supply chain expert. He's in York University. So a lot of different features, and the model takes in account of a lot of different features, and we manually annotated that. We know the machine didn't do anything. We manually annotate. So when you, again, the doctor's office example, the doctors were, uh, serving the data, and they annotated this person has COVID or not. Or maybe in your case, I looked at you and I manually annotated. The annotated data builds the foundational model. So someone actually had to manually go ahead and annotate it. So this is an example of supervised. Whereas your question regarding clustering, it could, sorry, my mouse froze here, just 1 second. It could also have all of that, ethnic background, it could have all of that, but we did not tell the model if the person liked samosa or not. The models, the model's job now here is, without us telling it explicitly, it needs to find if someone likes samosa or not. So maybe it will find trends. Like, for example, maybe it will look at things like, oh, York University supply chain, based on that, your vector space or your distance to samosa is shorter. I mean, this is not a perfect science here of the example I'm giving you, but it will automatically recommend you. One of the things that they do is, so what they do is, for example, if you, let's say this is samosa, and this burger and ramen, or things like that, and it will put all the people here, and there's a lot of different techniques. It's something Euclidean space, there's cosine similarity. It will look at the data and it'll say, the construct of the samosa, Adil is somewhere here, hence he may like samosa. So the math behind it is a little complex, but what the point I'm trying to make here is, in supervised, you're telling the historical trend of a lot of people. In clustering, you can have as many features as you want, but you're not telling if Adele likes samosa or not. So the machine will be forced to learn on their own. Does that make sense?
Yeah, thank you. Yeah.
So the idea is that you're just letting the model do the job, and which is kind of fun and kind of thing as well. Like the other example I can provide is, um, for example, like if you're in a physical class, and then we open the physical class, and then you all go sit in the back side of the room, front side of the room. There's a reason why you sat close to each other, right? We didn't tell you where to sit, but maybe you guys are commuting from same location. Maybe you have similar ethnic background. Maybe you have like you have same educational background. There's a reason why you're sitting close together. The model will try to identify what are those similarities and cluster it without even knowing. So that is one of the things that it does. The other aspects here, you'll see, like, I'll just quickly go through the slides here. Descriptive, we've done it. You did it as part of your sprint one, which is understanding the historical data. The second type, diagnostic, is simulation. We'll go through regression. Regression, again, estimating values. We're diagnosing, and eventually it The diagnosing also becomes prediction. And one of the things that you'll also notice is called time series data. Uh, Time series data we don't cover. I have some videos that I created from other class. I'm happy to share. Essentially, like for example, let's say you want to, if you're a supply chain guy, and this is the number of Mac computers sold last 15 years, right? And what is this? Is, you know, this is year, let's say year 2000 all the way to year 2024. And on the x-axis, it will have year, and then y-axis, it will have units, right? And let's say this is 50K, and this is 20K. So what this is telling you is that year 2000, it was the sell price was less than 20K, and eventually by 24 it has more than 50K. So time series data has time and unit. So the distinction here being is that you are able to predict an index, or your choice of your dependent variable, which is units, and depending on the year. So as opposed to the other stuff that we have looked at, time series has time element. And it's a very fascinating topic because, the temperature, your GDP, the students per year, all of these things have time element to it. There's a reason why we have more students in the last 3-4 years in Canada, because the policies are more supportive of international students. Perhaps in next year or so, the policies will be coming down and we'll have less students. So the time series gives us like a good context from economics point of view, and how we can look at things. It also gives us trend. Is the trend of Mac computer being sold high? Perhaps. Is there seasonality? Are Mac computers being sold more often on December versus June? That's something that we can identify. So it's just a little bit of off topic here, but if you're this is what it is. And I'm going to avoid going through very specific things, but this is just if you have clear distinction between regression, classification, and clustering, other things are supporting of these things as well. So same thing here. So a lot of times we've looked at certain things, and we've said, looks like the machine learning and AI and all of these things are new, right? I heard about it less than 15 years ago. I mean, I knew for me, the AI part was around 10 years ago that I was more aware and more prone to learning. If you told me 15 years ago what is the AI, I would have no idea. But what I'm trying to put the point across is that AI analytics, whatever you call, is based on statistical foundational models. And these foundational models have always been there, like 4, 5, 6, 7, sometimes before the time of Da Vinci. It's always been there. What changed in last 15, 20 years is our ability to process large amount of data very quickly. So, if you think about it, if you're 400 years ago, and if you had sampling data of about 5,000 people, you had to manually calculate that because there was no computers. Last 20 years, we have supercomputers. We have a lot of data. That is why our models are getting smarter and smarter, because they now can access a lot of variety of data. So the point I'm trying to make here is whatever we're doing is based on statistical modeling. If you are just using how many samosas are people going to eat, and you're basing it on average samosas consumed, well, that is also a statistical model, right? Because you're using a mean, a descriptive statistics to create a model. So the model, the box that I've been showing you around, is based on the idea of some math, some probability, some random variables. It is technically based on math. The beauty is a lot of this mathematical modeling is done by computer, done by Excel, done by Python. So we don't really need to sit down and calculate. We just need to know why it made those decisions. That is kind of important. We touched on this as well, is there are two types of analysis, univariate and multivariate. You've done both, and I can attest to that. Is that univariate? If you're looking at a wage of someone, a wage of a demographic, let's say this class, let's say I calculated all the, I surveyed your information, I put it in Excel, and every student I assigned a column called wage. Some were making 100, some were making 200, some were making 50, whatever. So just that particular column is a univariate analysis. So from that wage column, I can see how much money on average the students are making, what is the dispersion, meaning, you know, is everyone making the same amount of data, let's say, closer to the mean, or is someone making $1 million and someone making 50,000, maybe big disparity. I can also look at where a lot of people make money, you know, are clustered around. So it kind of gives me a distribution. So I'm strictly focusing on the univariate or one variable in that sense. That is a univariate, which you've done. Multivariate is, let's look at the same data, and you have wage and you have years of education, for example, and it's another feature or variable that you have. And years of experience are numerical values. So, you know, some people have 15 years of experience, some people have 5, some people have 1, and so forth. And now I am going to see the relationship between the years of experience and the wage. And I can do regression models, which we haven't gone. I can do correlation. I can do seeing the distinction or differences between, if one goes up, what happens to the other. Now, what we have just done is called multivariate analysis. We're looking at two different variables and trying to find some sort of trend or a correlation or some sort of coefficient to address that. So statistical modeling does all of these things as well. All right, it is almost an hour. I want to not be you know, going on and on without giving you a break. So let's take a 9-minute break. So let's convene back at 10:35, and we'll continue with this discussion. And hopefully I'll be able to finish this on time. So I'll pause recording, and please be back at 10:35. Thanks a lot. Okay, so same thing about the data mining. Essentially, it is the idea about it's mostly you're looking at it to find some nuggets of information, patterns, some natural language processing, some statistics. So it is, you know, it could be structured data, it could be unstructured data. I'm not too sure if you know the distinction, but structure could be something in tabular format. Unstructured could be your free text, the comments you write on email, those kind of stuff. So you're looking at a lot of different information and trying to find important information. One of the things that ChatGPT or Copilot does these days is if you feed a file, like a PDF file, especially Copilot, I'm not too sure about ChatGPT. Actually, it's probably the same thing, different flavors of environment. It can summarize and give you the most important text or information. So that, like, you know, extractive summation or overall summation based on large amount of data. That is something also an example of data science, sorry, data mining. And it is intersection of computer science, statistics. And at a very simple level, you're looking at large amount of data and how we can you know, bring it down or synthesize and really drop it down to a smaller amount of data, and from that we can find and tell. So data mining, some use cases, is essentially to find patterns. Some patterns could be not interesting. Some patterns could be spurious or inaccurate. Some patterns could be garbled or missing. And obviously, it is a very refined process, right? Let's look at one example that we have here is um, based on someone else's survey, we captured the information, and the leftmost column is outlook, temperature, humidity, windy, and play or no play. Now, to my earlier thing, if you wanted, and we'll talk about supervised and unsupervised in a bit, but this particular item, someone had to annotate it. Like it just didn't. If we call this training data or data that is used for modeling, someone had to, put this stuff, right? Someone actually had to annotate or label that. And these are all categorical variables. None of them are numbers: sunny, hot, high, false. Now, if you wanted to create a model, you can create a model something like this, where you have a lot of conditions. If outlook equals sunny and it is humid, is high, then play. You don't want to play, right? So, sunny, high, do not play. And you can create a lot of conditions like this. And this in itself could be a model as well, right? So this is example. Now, if you wanted to create a machine learning model, it also works. What you could potentially do here is make this a dependent variable, and make these guys independent variables. So based on these 4 conditions, you can predict if this is going to be dependent, or sorry, someone's going to play tennis or not, right? So this is one example that we have. So in this case, we are looking at 2 different kind of rules, and don't confuse classification rule as a classification as a context. But really, what this is trying to tell you is that you're predicting a value of a given outcome or attribute based on previous information. In other words, if you had outlook and humidity as variables, maybe predict if someone's going to play tennis or not. Similarly, we have something called association rules, and it looks at a lot of different variables, in the sense that it will look at, for lack of a better word, association, how it's associated, and also correlation. So in the second example, it talks about temperature, humidity, and it also kind of combines the humidity and windy, and looks at a lot of combination of if statements to give you some sort of idea. Another example that we have here is we could also incorporate in our model numerical value. So in the previous example, we'll say the temperature high, low, that kind of stuff. Now we're giving explicit numerical value. So what I'm trying to build up here is that a model could have combination of categorical, sunny, overcast, rainy. It could also have combination of numerical values. And in this case, it is a discrete numerical value. You could also have continuous and so forth, right? So based on that very little example that I gave you, is that the data mining you could think about really almost everything. You could look into it from a loan processing. You can look at image processing. You can look at industrial uses in machines. You can look at real life sciences like biology, astronomy, so forth, and so forth, right? One of the real use cases that I use when it comes to data mining in my application on a day-to-day work is what I do is I work with a lot of technicians that are out of the field, and they climb towers. I'm a part of the utility sector. So when they climb towers, and when they're done with the climbing towers, they come out and they write a note on SAP environment saying, to close the work order, they'll say, oh, we climbed the tower, it was good, it was bad, whatever it was, and they go home. One of the things the manager wants to look at is how can we look at their opinion, their ideas about their experience, and use to improve the safety of the organization. In some cases, you find a lot of resentful comments saying, oh, it was very slippery, we didn't have adequate equipment. In some cases, they are pretty confident and happy about the experience. We can, and these are not just 1, 2, 3 techs. We're talking about thousands of technicians on a daily basis doing many, many different jobs. The challenge is if you are going and reading these comments every day, you may forget. You need to keep track of it. There's a lot of analysis that needs to be done. So what we essentially end up doing here is we process these data in bulk using combination of statistics, computer science, data sets, and we formulate synthesized, conclusive comments or summaries that we can use. That is an example of data processing or data mining. Some other examples that we can, look at is example 1, process a loan application. And if you are doing a lot of qualification of mortgages now, they ask you a bunch of different questions, like, what is your household income? Did you default in the last 5 years? There are a series of questions. And based on that it's a model in the back end trying to tell you and the bank that if this person is suitable for a loan or not. You could have a lot of different, variables here, but the real business question is, should money be lent to the user? And then some of the issues that you see here is, you could use a statistical foundation. Yes, 90% of the case where, they were given loan, but the problem is, if you said yes to 90%, but then 50% of the people defaulted or did not pay back the loan. So how do you create a solution on this one? You can create a model to find nuances that alert you that the consumer is not going to pay the loan. And also, and these are things we don't know. And one of the things I want to emphasize is sometimes our eyes and our intuitions lie. Something may not be as obvious as what we can look, right? For example, what I mean by that, we're like not our human mind is not multidimensional. What I mean by that is, if I asked you, how long does it take from you to go to York University to downtown Toronto? Well, you'll be saying, all right, it is about 30 kilometers on a good day, 30 minutes, on a bad day, 1 hour. Boom. That is your analysis, right? Or that is my analysis. And one of the things that you will probably say, oh, the highway is bad. And, these are obvious, inferences or assumptions that we make, and it's probably correct most of the times. But machine can look at multi-dimensional data. It can look at the gas uses, the model of the car, the slope of the roads that you're riding on. It can predict, just like Google Maps predicts the traffic on the hour. So it can capture thousands and thousands of variables, believe it or not. And it could say the time it takes from you to go from York all the way to downtown. There are about 1,000 variables that can make a difference. And out of those 1,000 variables, perhaps you pressing gas 5 times more often on an average in an hour or every 5 minutes, or the quality of gas you're using, it makes a difference. It can kind of give you things that you thought, oh my God, I didn't even think about those things. Because the model will look into a lot of different combinations. And based on those combinations, it can say, this is the most important variable. That is the difference between us and the model. And that's why we use model. And when I say model, computing strength. Um, they're only humans are still very smarter than an average human, or even a, any human is much smarter than computer. Absolutely, there's not even a debate. I think in 70, 80 years we'll see that gap being decreased. But what machines or what computers or what models, whatever you want to call it, does better than humans are two things. It is amazing when it can do repetitive tasks, same thing over and over again, and it has an excellent memory. Those are two fundamentally superior things that the computer does. And because they have that, they can look at a lot of different data. Our memory will only serve certain things. And it also can repeat the calculations based on different variables quite often. So my recommendation is, when if you watch baseball, cricket, soccer, they call about data analytics, data driven. When you're watching soccer, you say, oh, Ronaldo should have played like this, or Messi should have played like this. Perhaps there's another factor that's dictating, right? So now going forward, when you're doing analytics, you should really focus on um, understanding what variables impact more than the others. That is the advantage that we have. So in this example that we have, maybe we can identify certain aspects of lending process that is counterproductive to the business, in the sense that 50% is defaulting. The other is like, for example, business question is, what is the expected load for normal climate? And then we can adjust the load forecast. And if you are working in the electricity sector, anywhere in the world, electricity cannot be stored. It can only be transferred. So a lot of times in hot summer months or really cold months, there's a lot of outage because the demand cannot be kept based on the so in other words, we don't know what the demand is going to be like. If you create a lot, you're wasting resources. If you create a less, there's people are going to have an outage. So what is the forecast? What is the optimum zone where we can have little decay or little somewhat good uses, and more or less avoid outages, right? So the modeling could also give you some idea about the holiday effect, how much load you can do based on the previous data. So this is another use case that we can use in machine learning, which we call forecasting. Sometimes some of the attributes or features or independent variables could be climatic information, temperature, humidity, wind speed, and how can we assess that? We can see what the load was and what the predicted load was, and if it's very close, then your model is somewhat accurate, right? So I'm just trying to build up some use cases on how to do these things. And again, like a lot of companies do this, especially on institution. I've seen it in universities. Is for example, or in marketing, is they'll send you a lot of emails about email marketing, and if you don't respond, you go into a different table where you're labeled no, and if you respond to one, you'll be saying yes, and they will trend it over the course of a few months, and the yes group now is more likable to buy the product. So you're totally ignoring, you've been filtered out. So you can also look at it that way. So you're kind of, and then based on the yes group, now you can understand what are the demographic, what kind of, are people responding more because they're under 25 or over 25? Perhaps they have college education and so forth. So they can do a lot of analysis based on very minimum data that you're given, because they're privy to large random sample size of data from all over the place as well. In this example, you could create some association techniques, find people or groups that tend to go together, especially if you look at Amazon. They have something called recommender system. If you buy a hair gel, then they'll also recommend you hair color. I don't know, something like that. If you buy mortar and pestle, they will offer you like, I don't know, like kitchen mat or something. So there's always historical analysis or historical association that happens as well. So, the data on this table that you can see is that, when I say predict, we're talking more on the estimation part. Classification is something that we use as classification and clustering. We didn't really talk about reduce and association, but these are also these are more of a data. um the reducing is also more of a resource kind of thing. It's not, although it is unsupervised learning, which again we'll talk about in a bit. It's about creating or shrinking the data in some ways. It's more of a resource thing. But these two you should always remember: predicting or estimating, classification, and clustering. Association is more on the not purely machine learning model, but it's a capability nonetheless. So when it comes to machine learning, predicting, classifying, and clustering, reducing allows us to reduce data, which is also important, but it doesn't stand in itself, in the sense that the reducing model does something, but it's not really super impactful to our discussion here. Going back to the same thing, again, we're going back and we're still hovering around the analytics portion. So at this point, we talked about if you wanted to predict something, you need to have features. Without that, it is not going to work. And and the whole foundation on how we're going to create model and predictions and things like that is about, we need to have set of rules. It could be your basic if-else statement. It could be learning data from various different modes. It could be your own model. It could be anything. The model, the little model box, is for you to figure it out. I mean, there is competent existing models that have always been in the place, that have always done a fantastic job because it's been vetted and peer reviewed for many, many hundreds of years. But this is not to say that, if you have something new, it may work. You just have to prove it that it works. So we go into machine learning, and by definition, the machine learning definition was initiated almost 65 odd years ago in 1959. And Arthur Samuel is often called the father of machine learning. And I'm going to quote unquote him, is that the field of study that gives computers the ability to learn without being explicitly programmed. So what does that mean? Like, I'm going to draw it out, and I think it makes probably more sense. Is this is data, right? Data, and the data could be supervised and unsupervised. The learning could be supervised, but we give the data to a machine, a computer, right? A computer. We tell the computer, learn from the data, do something about it. How do you learn? Well, first of all, you can see the correlation between the two. You can see the relationship between the two. You can see the association. Whatever it is, learn from it. Once you learn, this is going to be a model. And once we feed new data, new prediction, let's say Michael Jordan's height, sorry, not Michael Jordan. Let's say, we predict, three people's height, new person. And, let's say Adele, we look at his, parents and grandparent, and we put the information, and the model based on this previous learning will be able to predict something. We're not, so what does meaning explicitly program means that without being explicit, we're not telling model to do something. We're telling model to learn from the previous data and then make the prediction on their own. What is happening with machine learning, especially machine learning, there's three things you need to understand here, is that One, you'll be given data. And for it to be machine learning, the data needs to be trained. Okay. Trained meaning, let's say you are running for a marathon, and for you to run a marathon on September 1st, you had to train. And how do you train? Maybe you run in Mississauga, run in Niagara Falls, run in Etobicoke, whatever it is. So you're running different places. You're running at 9 a.m. You're running at 10 p.m. So this is the training. This is where the model is trained. After the data, after you run the marathon, you'll be tested. Okay, tested is September 1st. Okay, so think about this context, and let me go back to the data example. So you're given a data. This 80% of the data, and 80% is a normal standard number, is given to train. Meaning the model will learn everything from this data. The model does not know it exists. So once the model is trained, we make it a model, and the data it hasn't seen, we'll feed it and ask to predict. The evaluation of model is on this guy, on this test type. Just like, let's go back to the example of the running marathon. First, you ran everything, and really how well of a runner you are is based on how well you run on September 1st, correct? Because that is the official run date. Same thing with the machine learning. Machine learning does, again, I'm sorry if I'm being a little confusing here. Machine learning is about learning from given data, and after it has a mind of its own. And once that is learned, now it is capable of doing something, right? So explicitly machine learning is to get knowledge by study, experience, or being taught. In this case, being fed data, to commit to memory. These are a more fundamental way of how we define learning. So the machine learning exactly is that there are components of machine learning. Is first of all, you need data and you need algorithm. Right. And then once you have that, you create a model, and the model is now used to predict. Right. So the source down here is machine learning allows the user to feed a computer algorithm with an immense amount of data and have the computer analyze and make data-driven recommendations and decisions based on only input of data. What that means is, again, you create data, you have data, the data is fed and trained in an algorithm, and the algorithm, both of these combine to make a model, and the model is waiting for you to feed data or ask questions, rather. That's a better word, right? And you ask questions. Once you ask questions, the model will recommend your thing, right? Okay. Any questions, folks, so far? If it's super quiet, it is also a good thing and also a very bad thing. So, okay. So without going into whole, the slides here, is that it's a field of computer science, and it has been around for a while. It needs data, it needs some sort of algorithm, and the algorithm that we're going to learn today is called linear regression, but it could have a whole different varieties of algorithms, not a problem. And if you think about, like, if you go to Gas Buddy, or if you want to predict, if you see a lot of these predictions, this is based on historical data. So a lot of times you've already seen machine learning at use on a daily life, um, which you didn't know that it existed, but it's always been there. Some of the advantages of machine learning is once the training data changes, the model is also going to tinker a little bit, change obviously, because it's always continuously learning. It is also a reliable way of presenting things, right? What I mean by that is, we have a process. We're not just guessing. We know exactly what needs to be done, right? So machine learning, on a bigger AI point of view, it encapsulates few things. So when someone says AI, it has many branches, machine learning being one of them. So there's ML, machine learning, there's NLP, natural language processing, the ChatGPT is NLP, and there's also going to be reinforcement learning, like robots and so forth. So this is what we're talking about. AI, ML, or machine learning, is a subset of AI, which is a bigger domain as well. So again, back to the point of supervised and unsupervised. So supervised, you have labeled the data. So if this is Adele, Judy, Alice, and so forth, and this X1, X2, X3 are preferences. X1 could be ways, X2 could be A's, P means you can have as many variables. Let's say X3 is the years of university years or academic education that you have, and Y is either you like samosa or do not like samosa, right? So we've given this data to the model. Now the model will learn based on, so if, master's degree, 5 years experience, making $200,000 a year, like someone says yes, and so forth. So the supervised is the fact that they know the outcome. So when the new data comes in, it will understand the thing from the learning. Unsupervised, we're not giving the preferences of Adele, Judy, and Alice, and so forth. We're just giving the information. Both have advantages and disadvantages. This is labor intensive because someone had to physically label the data. This is something that we think it automatically happens in AI. No, it doesn't. We have to label the data. The machine can only learn so much, right? Machine has to be given instruction, right? So unsupervised, we're not giving that why. We kind of talk about. Like I mentioned, the task of inferring from a label data, it's also called annotated data. You're given the annotated data, it will look into it, it'll look into the relationship. I'll show you what that really means with a live example, which is linear regression. And after that happens, now the model is ready to identify trends, patterns, some of the relationship, and so forth. When we give that Adele, Judy, and Alice's data, we call that training data, obviously, because the model now gets trained on the data. And the model also needs to be evaluated, but when we want to evaluate, obviously we need to do that before we bring it to production. And that is where the test, entry, and set comes in play. Technically, we don't need to, if we decide not to evaluate, it's also fine, but there is no validation or confidence that it's going to work well as well. So that is an example of supervised. Unsupervised is unlabeled. We're just throwing it out there and then letting the model dictate. The advantage, again, is you don't need to be laborious when you're constructing the model, because the idea is that the model will somehow find its way. How do you distinguish? If you don't see, depending on the algorithm you're using, and also If you don't see any annotation on the data, that is a giveaway that it is unsupervised learning.
Quick question. Yep,
Yes.
sorry. So can we have similar outcomes for a cell? So let's say, I mean, similar data for both unsupervised and supervised learning. Can we have similar outcomes from the both learnings?
Yeah, so like for example, they are intended to do two different things. So for example, unsupervised, you're mostly trying to see clusters of people. Like for example, without you giving instructions or let's try to get back from the start. So if you're doing estimation, regression, and classification, the estimation or regression or classification, without you telling how the historical data looks like, it is impossible for for the model to predict because it has no idea. Unsupervised in the other one it's looking at a really different thing. In other words, it is only trying to more or less calculate the clusters in most cases. Um, the friends that you are closer with when you sit together in the class, it won't tell you your ways or age. It'll just tell you how well you are connected to a certain friend. Let's say, for example, Alice or me. If you're constantly sitting next to me, it means that it is identifying or solving different kind of problems versus classification. It tells you if you are going to pass the course or not, and estimation, it tells you if you're going to make more than $500,000 or not in a few years. So my point being is that these learnings are positioned to solve different business problems. So to your question, will they give you the same outcome? Maybe clustering and classifications kind of similar a little bit, but they are positioned for totally different learning outcomes. I don't know if that makes sense, but let me know.
No, I think that makes sense. I think though, so these both learnings are two different, completely different, like
Yeah, so
processes, I guess.
yeah, the most simplified way of looking at things is, if you wanted to, if you wanted to go on 401, you want to ride like a regular vehicle. If you want to go off-road, you have to ride ATV. So unsupervised learning is adequate if you are trying to cluster data, reduce resourcing. Also, there's no way for you to label the data and so forth. So it's a very different purpose. Whereas if you wanted to know the price of gas, you had to know certain attributes. You had to know, someone had to label the data for you, right?
Yeah, thanks.
Yeah, no problem. Some of the things, the machine learning, now we're talking about the models itself. What encapsulates the model? So, again, you have the model, but the model is foundationally based on some sort of algorithms. And we'll talk about a few algorithms and specifically linear regression. And I'm going to kind of draw this out. I think the best way to do it is what the linear regression works, right? So I'm just going to draw it. Give me 1 second, and I hope I don't. Okay. All right. Right. So let's say this is y and x-axis, and y is always a vertical, and x is always going to be horizontal. In any model, any statistical machine learning models, what you are trying to find out, we always call it y. What we are trying to find out equals y. Always, it's always the thing. Now, let's say we have two variables. One is called wage, and the other one is called age. Okay, so just to summarize, you have y and x-axis, and wage is how much someone makes money, and age is their age. And we went to Stats Canada, and Stats Canada gave us a database, something like this. And it had information about, it has two variables, or you can have as many variables as you want, but for simplicity, we had their name, we had their wage, and they had age. Okay, let's say Stats Canada gave us 10 observations, meaning 10 entries of people. We want to create a linear regression. All right, so first thing we want to do is, so let's say, first, someone's wage was 20. I'm just doing it in someone's age was 30. So, let's say, hypothetically, guy named Joe, his wage was $20,000 and his age was 30. Ali, his age was, let's say, the wage was 30,000, age was 25, something like that, right? So we had 10 different data. Once we have the data, to create a linear regression, what we need to do here is, so this is always a 0, and the intersection is always a 0. And when you move up, it increments. So let's say this is 100. Let's just give us a scale. Okay. And let's say this is 40, just to give us a scale. Okay. So what we need to do to create a linear regression is Joe, his wage is 20 and his age is, let's say this is 30 here. Okay. So his wage is 20 and age is, let's say this is 50 and let's say this is 20. Okay. So his wage is 20 and age is 30. So 20 somewhere around here and age is 30. We make it a mark. Let's put that X. Second guy, his wage is 30. Let's say this is the one somewhere here, and age is 25, right? And if you have more and more 10 values, we will be kind of doing something like this all over the place. Okay. And let's say we have 10 examples here. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So what we did here was we created some sort of correlation between wage and age. The fundamental thing about linear regression is what we call this dots is observed, meaning it has happened. Observed values. And we map that, right? Now we can see we have some idea about the data where it rests. What we can do now from a linear regression point of view here is we can draw a line, something like this. We draw that line and we keep in mind just one thing. The line in some ways has to be very close to all data points. If the line is very close to data points, all data points, not just one, what does that mean? It means that the line is representative of this sample size. It means that it may not be super accurate, but it at least is very close to the real observation. Now, you created this model. This is a model. Now it's good to go. This is supervised. This is linear regression. You were telling explicitly who's going to go where. Now, this is your analytics company, and you created a model based on Stats Canada data. And now you start a company and you say, if you want to know how much people are going to make, come to me. I'll give you that information for you, right? Now, someone from the street comes and just says, hey, I want to hire some people, but I want to know how much wage they will be making because I only can afford a certain amount of money. And they say, I have a very experienced person who is 50 years of age, and I want to know their wage. So a linear regression is, so now 40, right? So we can, but we only know data until 40 years old. We don't know data about 50. We just know about 40. So what do? Well, we look at the slope of the line. So if the slope of the line continued, and if the x-axis continued 50, where would it meet? It probably meets somewhere else. And we can say the wage is probably going to be like, let's say 40K. How did we know that? We were focusing on the slope of the line. How was the slope of the line created? Well, the slope of the line was created based on the idea that it would try to go as close to the observation that happened, and it went so that it can create some sort of trend for you. Is the model super accurate to our earlier point? No, because if you're trying to guess someone else's wage around 31, 32, it is going to be inaccurate because there's a lot of gaps. But if you're trying to predict someone's age, a wage around 38, it is accurate. The construction of the model line is a mathematical process that we don't go in the course, but sometimes, most of the times, it is called OLS, ordinary least squares. In other words, it has a math behind it to tell you that to draw a line such that it tries to minimize the error. So this is an error. This is an error. Collectively, not just for one, collectively minimize the least amount of errors. So if we do that, then the line is somewhat representative of the 10 samples that we created. So this trend is going to go. What happens when someone is 100 years old? Do you think this model is going to be accurate? I'll hear your opinion on that one. 50 years, it may be accurate, but what happens if someone's 100? Looks like if it's 100, it'll continue to go up, right? Is that an accurate model? Just give it a thought. Like, if I'm saying that this trend has to go all the way up, is that an accurate model? What happens when people are past 65? Their earning potential kind of decreases, right? Kind of goes like this, and they retire and probably never going to make as money. So this model obviously is not going to be working for every age. It's probably going to be only working for people of certain age. So obviously, I'm just trying to present some of the limitations of the model as well. That's why we say sometimes, we have to be mindful of how the models work. It may be accurate when people are around this age, but it may not be accurate when people get older. But this is an advanced linear regression concept that sometimes we can also draw a line so that it kind of curves like this, right? So the drawing of line is important. Why do we create a linear? Because this is linear. It's a line. So when this guy goes 1 unit up, this also go 1 unit. When this guy is 2, it has a consistent trend. It has a straight line. But nothing in life is linear. You go to your spouse, you treat them well, you buy, you take them out, and then he or she is really nice to you. Tomorrow you do the same thing, they're really nice to you. Third day you do the same thing and they're really mean to you. You have no idea how. Why? but there are other factors that might be encountering. So something like that, linear regression does not always hold true. Any questions on the preview of the linear regression? What we're trying to do here? Essentially, we're establishing relationship between two variables or three variables or four variables, multiple variables. Logistic regression is about classification. Someone has disease or not, one or two. And the decision tree is a decision tree that you have looked at, like almost like the organization structure, right? We don't talk about these guys just yet, but I just wanted to give you a preview. If you wanted more in depth, you can watch this video as well. And then I think I also created a video of mine on how to do linear regression. But the real foundational thing about linear regression is also based on this mathematical function that you may or may not have seen. It looks fairly complicated, but it's not. And I'm going to try to simplify this a little bit. Okay. So again, y, whatever you're trying to find, y is going to be on y-axis vertically. And whatever you're trying to find is going to be x. Okay. We had some observations. And we drew a line, something like this. Let me try to draw a straight line. Okay. And we call this x1. And we can also, so let's just kind of limit here for x1, but what this is telling you, if you wanted to find y, you need y-intercept. This stands for y-intercept. You need, ignore this for now, you need beta 1 times x1. What does that mean? Well, forget about everything. This equation does not exist for now. You created that wage and age data, and you, with the observation, you drew a straight line. The line made sure that it does everything. Perfect, boom. The y-intercept, the b beta O, means that it's this point here. What does that mean? Is that if x1 was 0, what is the minimum value of y? Okay, in other words, if wage, so if we're looking at wage and age, if age was 0, what is the minimum wage? Although it sounds unrealistic, this is what it is, right? Because sometimes, if wage and age, think about this way: if age was 0, meaning age of or like a experience, if experience was 0, you're still going to get money, right? I mean, although for the first example, age, it sounds realistic that how come someone who is like not even born going to make money? That is like a little, weird thing about the model. But if you look at it from a different example, it makes sense. If people will still get money, right? So what this is telling you is that if they did not have any experience, what is the least they're going to get? And looks like it is they're going to get 10. Now, but if they start having experience or age, what kind of impact does this have on the y? Let's say if it is 0.5, it means that, so let's say it's 1. It means that anytime this moves, this equally moves. If it's 0.5, it means that anytime this guy moves by 0.1, this guy moves by 0.5. It's just a mathematical function. It's just a multiplier of some sort, right? Now, the wage and age is another like a very one-to-one relationship. In some cases, you can also add another variable called x1 or x2, right? x2, this is it. Because not only your experience, your ways could be impacted by age, it also could be impacted by education, or sorry, let's put it experience as well. So although it sounds super confusing here, the takeaway I want you to put is that you have a function. The function encapsulates y-intercept, the minimum amount when these predictions are 0. It also can incorporate the influence of x1, age. It can also incorporate influence of experience, x2. And if you wanted to put like, location, whatever, this can go into perpetuity. You can have 500 different variables, right? Questions, folks? I would love for you to, get this clarified before we move on. No questions? Thumbs up if it kind of makes sense. If it doesn't make sense, I'm happy to go at it again. Okay, there's 2 people. All right, so most of you. Okay. So, I mean, this is how, this kind of looks like, right? So if you look at it here, if you want to predict the GNP variable, you can have multiple different features. So for example, this could be X1, this could be X2, this could be X3, this could be X4, X5, X6, and X7 as well. So you can have a lot of different variables. The year, it is, sometimes you can use as a categorical variable as well. So it's really, so you can have 10 different variables. So the best part is now you will quickly realize which of these guys will have a very strong influence on this guy. So that is the beauty about linear regression. And if you want to visualize this, this is how it would look like. You would have one y, and you would see influence of a lot of different lines, and you add these lines together to give final value of y. Okay. So if you look at the equation number 1, this one here, GNP, if everything else was 0, the minimum value is going to be 1338. How do you know that? Because if you put 0 on all of them, well, this is the minimum value. If there was no accrued, no interest, no foreign. But if you note here, looks like the interest has a very big influence, because look at the variables here, the multiplier. So if you wanted to guess the GNP of something, if someone now, your model can be, the first model, if someone said GNP, try to tell me GNP when, now your model, try to tell me GNP when crude is 5, interest is 6, and foreign is 5, right? So if someone would tell you that, then all you would do here is 13.1338 plus 3.74 times 5 plus, and it could also sometimes be negative as well. Negative, it could have a negative influence as well. If you remember correlation, 6 and plus 12.59 times 5, right? So if someone said, try to tell me GNP when crude is 5, interest is 6 and 4, now you can calculate those things because the model, you created this model. The hypothesis testing, I will create a video. I think it is a very long, heavy topic. But the second model, you're just encapsulating one variable, only foreign. In the first one, it will have multiple different. Now, so generally, what do you call this? 3.7, 18.2, these are called coefficients of linear regression, estimates, base starting values, right? These will dictate how much of an influence it has on the overall model. If you use, if you notice here, crude foreign has 12.59 influence on the GNP for the first equation, but for the second one, it's a little lower. So it is normal to have a different influence. So for example, think about this way. If you had only one best friend, and you would have a lot of influence on the best friend. But if you had three very good friends would have a different kind of influence on you, right? It may not be as high as having a single friend. It's kind of like that. So moving on, this is what I showed you, is that the drawing of the line is going to be what will dictate you. So fitted means the line you draw, you fit the line, you created the line, you fit, like, you ensure that you fit the thing, right? When you're like, if you're getting a dress or a suit for your wedding or whatever, it has to be fitted. It has to make sure that it is running all the way up, right? The dots are the observed. So if you note the red lines, it is trying to go as close to the dots. What that means is that if it's close to the dots, the model is somewhat inaccurate. If you note that one of the problems with the model is it's very accurate when it is dealing with data around this zone, but it is little less accurate when it goes here. And how do you know that? It's just because of the shape of the thing. I mean, this is not desired, but this is something that is going to come across. Okay, logistic regression is a very math-heavy concept. But what this is telling you is logistic regression is only used. So I'm going to go back. The linear regression is used to predict, one more back, to predict the value, the numerical value, right? So it is not going to be 1, 2, 3. Logistic regression, in the other hand, it uses probability and log of the odds ratio to predict if someone is going to be COVID or not COVID, pass or fail, and so forth. I'm going to again go back here. I want to show you something here. This little chart. So what logistic regression does is, if someone is in COVID, they will be in this zone. And if someone's not in COVID, they will be in this zone. So they can say 1 or 0 based on this one. Whereas it will segregate 2 classes, 3 classes, whatever it is. It will try to categorize blue, black, yellow, yes, no, pass, fail, and so forth. It sounds complex. I hope, maybe next week when we meet again, I will try to emphasize that. But logistic regression is also extension of linear regression, in the sense that linear regression can go forever, whereas logistic regression, you bound it. So meaning that the values are kind of bounded so that you can get yes or no, pass or fail, and so forth. So I don't expect you to kind of just have that idea or grasp right away, because this is something that perhaps we need to focus later. So for example, if you look at the one thing that you definitely should pay attention to is that if you are trying to predict admit, what kind of variable do you think, or feature do you think this is? This column here, admit. Do you see a trend? Throw it in chat if you wish. If you notice, there's only 2 values, 0 and 1, binary, and it stands for yes or no, meaning if someone was admitted to school or not. And they have 3 features, GRE, GPA, and rank. And n equals 400 means there's about 400 entries or observation. The sample size is 400. So if you wanted to predict this, you cannot use linear regression, because linear regression gives you value. You have to use something called logistic regression. So it can dictate, it can tell you if it's going to be 0 or 1. So logistic regression kind of gives you the same coefficients, but ultimately what it does, it will say X, this person is either going to be 0 or 1. We call it bounded. It will either tell you it's a 0 or 1. It won't tell you 0.5, right? It has a certain threshold. So if you look at the the different probabilities, it's saying that the probability of someone getting into school from the first model is 73%, second model is 58%, 42%, and 37%, based on different ideas. So based on their rank, based on their information. So based on those 4 or 5 information, it can give you the idea, right? And most of the times, the scenario 1 and 2 will be labeled 1, and scenario 3 and 4 will be labeled 0, because the idea is that if it's more than 50%, you label it 1, and vice versa. I think I will probably make a little 5-minute tutorial on this one, logistic regression. It's a concept that takes a little bit of time. It looks like a lot of numbers, and we just don't have time to spend too much in technical details. But I think I will create a logistic regression setup on Excel and Python as well. The third one is called decision tree. And if you note, decision tree is something like your org chart. And decisions are based on nodes and leaves. And the idea of decision tree is, if you have a lot of data and you need to create a decision tree. What does that mean is that, let's look at this example, right? Like I'm just one of this example. You want to know if someone's going to be admitted to school or not. For you to create a decision tree, one of the things that you can do is maybe pick GRE as your first metric, and you can say if someone had GRE yes over let's say 350 or not, right? So if they have yes, they go to this side. If they have no, they go to this side. And once after you ask the GRE question, maybe you can ask the GPA question. And the GPA question will say, do you have GPA over 361? If they have yes, no, and so forth. Right? And after that, you can ask the rank question. So what this means is that if a new data comes in, you would be putting it here. And eventually, you can say if this person got admitted or not, based on that. Now, naturally, the question should be, how did you construct GRE at the top? There is like a very specific rules for that. And it's called Gini impurity score, meaning that it needs certain metrics to be at the top, which I will, again, not indulge in it. But really, it's very similar to your org chart where you decide it's a decision. It's almost like, for example, for most of us, I came to Canada. I was not born here. But, decision was through my parents. My parents said, oh, is our country going to be decent or not? And they said, maybe no. And the next decision was, which country would be open-minded about immigration? North America or not. They made sets of decisions, and ultimately Canada became one of our desired spot. So kind of like that. Again, I think I will eventually create a video on this one as well. So, but essentially you can, this is a Titanic data set. It's quite common. If you wanted to know who to survive, you can incorporate a lot of different decisions here. And if I go here, sex was the first deciding factor. And why did sex come about? Is because there's a metric that they use. And when you choose sex, male or female, as the first call, it was more accurate. And I think it kind of builds up an intuition, because I think females were last to leave on a sinking, one of the first prioritized passengers to leave, especially if they had kids and things like that, on a sinking Titanic ship, right? So same thing here. It's a bit of a read. Again, I promise to make videos for both of them. I'm going to move a little faster simply because we're running out of time a little bit. But one of the things about any models is something called bias and uncertainty. Bias means, let's say, I'm going to give you an example of a linear regression. If you have a model like this, right, and you created a line. and it looks like this model is going to be super accurate. What happens when you have data in here? It is going to be inaccurate. Why? Because it knew the training data so well that when exposed to a data it has not seen, it was severely inaccurate. That is a big problem. The other example is called variance. What if data was like this, and all of your training data was all over the place, and new data was kind of standard? It's also going to be wrong. So what I'm trying to think about, give you a real life example here, is think about this way. You have 5 friends. Let's say you only become super good friend with one person. You share assignments, you share work, you share life stories and so forth. And the 4 other friends, you are kind of unknown, like, they're there, but they're not really known. What if you lose your friend at some point, and now you are going to be uncomfortable, not able to predict what other friends are going to think? That is an example of bias. You're too biased about certain data or certain friends. Variance, on the other hand, is you're all over the place. You're not good friends with one, you're not bad, you're all over the place. Also not good, you're middle of nowhere. What a good model says is that you should be at a point where you are equidistant with a lot of different people. So all your 6 friends, you're kind of equal. So that way, if you see a data that was if you see a data that is new, it may be or can be very similar to what you experience. So in other words, you are neither super close with one friend or other, but you are close with all friends. And if you miss other friend, the other friend is kind of taking over, that kind of stuff. Being too biased in a literal form, you're too biased, you're not open-minded about different things. Being too uncertain or variance means that you're all over the place and you have no set philosophy or theory. Middle of summer, you're open-minded about bias, you're also open-minded of variance, you're somewhere in the middle. That model is going to be better long-term. And this has been proven over and over again through a lot of different examples. We call that bias versus variance trade-off or uncertainty trade-off. Somewhere in the middle is always going to be awesome. If you look at the technical example, bias, the systemic component of the error, and uncertainty, random component error, essentially both of them are going to get you in trouble. You need to be somewhere in the middle. If you wanted to know a little more information, there's a video, kindly watch that. Very quickly, you want to look at the linear regression. I kind of covered this in the video as well. Is the idea about, yes, you created this model, right? Like, I'm just going to quickly go back to the linear regression here. You created this model. How do you know if this model is good, right? One of the things that we can look at it here is something called R square, and this is R square. And these are bounded between 0 to 1. 1 means awesome. And technically, it means that this model is able to explain data. 0 means this model is not able to explain data. So in this case, if you look at it, it is over 98%. So this model is a good model. If this was more like 0.09, that would be a bad model. So that is how we evaluate the model. This is R square. There's a very long math behind it. I'll try to avoid that, but this rule of thumb is closer to 1, awesome. Closer to 0, not good. and this is how the values comes about. Um, there are other values, MAE, MSE, and RMSE. What they mean is that if you look at these uh, thing, the observation, and you draw a line, it means the difference between these, all of them in a different flavor or variations. The lower, the better. So all of these, lower, the better, because all of them are talking about errors, and errors. Mean absolute error, mean squared error, mean. Essentially, if the error is low, your model is good. Now, what's the ideal score? Well, you don't know. You might have to create like 5 models. And once you create 5 models, and you'll say, okay, model number 1 has the lowest MAE, MSE, and RMSE. Maybe this is a model to go. So it's a more of an evaluation metric. These evaluation metrics are more of a comparative assessment, as opposed to having a definite right or wrong number. Okay, you can learn more about these things through your these videos, or you can also watch the videos that I have created as well. But Python Lab is already created for you. I knew that I was never going to be able to capture all of these things in a one shot. So I did upload the video already. So it's 15-20 minutes. You could speed the video up if you think I talk slow or fast, whatever. Or you can just try it on your own, but hopefully you'll get an opportunity to do that as well. All right, so that's it. This kind of gave you some idea. I will make some regression and dysentery videos explaining the math a little bit, or perhaps there's already a video I can recommend you that. But really, with the conclusion of our engagement, you should be able to, between week 5 and week 6, run some Monte Carlo simulation, construct, know the distinction between dependent and independent variables, construct a linear function, at least construct it. The lab version talks about technical detail of what that really means. It's very specific, at a very, very specific level. So kindly watch that. And you should also be able to import data and run at least some models to get a feel for it. All right. I would now open, that's all I wanted to cover. It's a lot of content. Sometimes it's just not enough hours, but I want to open floor to see if you have any questions.
Vip, I have a question about the logistic regression and decision tree model.
Sure.
So, I mean, it appears as if like logistic regression model is more like a simultaneous evaluation of different variables, whereas decision tree is more like a filter out one variable at a time and then move on. So is there a framework that actually helps us say, okay, one model can be preferred over the other?
So for example, in terms of very good question. So for example, let's say logistic regression and decision tree. Decision tree, logistic regression only does classification. It cannot do estimation. Whereas decision tree it's also something called CART model, classification and regression. It can do both because it's just programmed that way. The first is decision tree is always going to be slow because, like you said, it's iteratively going through a lot of different options. Logistic regression is super good because we know coefficients, because we can tell which one created more value. Now, to your question, let's say if both of them are doing classification, which is their common thing, because one of logistic regression cannot do regression. But let's say if both of them are doing, I'm going to put DT, and LR. If both of them are doing classification, how do we know which one is better? We have three metrics, which we haven't covered at all: accuracy, precision, recall, and F1 score. So these are normalized scores that can tell you. For example, accuracy is how many things it got right. So it will be in a percentage. It will say 97% it got right, and then we can say DT got 96%, LR got 99%. Hence, LR is better. So to answer your question very shortly, the accuracy, precision, recall, and F1 score. When we're doing classification, we can iteratively compare not just these models, but any models that's out there. But I actually we haven't covered this in today's lecture.
Okay, thanks. That makes sense. Yeah.
Yeah. So it is a very normalized one metric, just like for your linear regression. There's MA, MSC. For classification model, there's another metric as well to compare these things. I'm happy to share some content on that one as well.
Yes, please. Thank you.
Yeah. Any other questions, folks? Okay, I think that's all I wanted to cover. Is there anything I could do to kind of simplify things? Is the video formatting okay, or should I maybe try to do hands-on more in the class? Or I figured that I was going to run out of time, and that is why most of the times I record videos, just so that it gives me peace of mind that I don't feel rushed, and some people, can do that on their time as well. So, all right, last call. Any other questions before you go and enjoy your fantastic day outside? Okay. All right. If no questions, I will stay for 1 minute, but have a lovely weekend. And when we come back, I think there's a presentation, but I'll communicate that through Moodle as well. Thank you.
Thank you.
Thanks, guys. Take care.